Greetings, everyone. In this video, we're going to talk about concavity and inflection points. These are features of a graph that are going to go along with the features that we've talked about in previous videos. And it's going to allow us to establish an important theorem called the second derivative test. Now, in the last videos, we had the first derivative test, and we used features of the graph regarding increasing and decreasing, whether the graph was increasing and decreasing, and we found out how to use derivatives to determine that. And then we used that to establish the first derivative test. So to get the second derivative test, we're going to use these notions of concavity that we're going to learn in this video. And this is all going to be very important because the second derivative test is the first thing that most people will just jump towards when they want to establish whether a function has a local max or a local min. It's the easiest test typically to use. And so that makes these notions of concavity very important. Anyway, let's go check these out. All right, so here we have the definition of concavity. A function can have two types of concavity. It can be concave up or it can be concave down. So let's read what the definition says. It says, let f be a function that is differentiable over an open interval I. All right, so differentiable means you can compute its derivative at every number in that interval, right? And it's an open interval, so it does not contain its endpoints, okay? So it's differentiable over an open interval I. If f prime, the derivative of f, is increasing over I, we say that f is concave up over I. If f prime is decreasing over I, we say f is concave down over I. So that's what it means to be concave up or concave down. A function's concave up if its derivative is an increasing function. Now, we talked about what it means to be an increasing function in the last couple videos, right? So make sure you watch those if there's any confusion on that issue. But we talked about what it meant for the function f to be increasing. Here we're applying that same idea to the derivative f prime. So we're not looking at where f is increasing, we're looking where f prime is increasing. And if f prime is increasing, we say the function's concave up. If f prime, the derivative, is decreasing, we say the function is concave down. Okay, so let's look at an example. Okay, so what we see here is we see the graph of this blue function, all right? And that's the function f. And at a point, I've also graphed the tangent line to that function, and I've illustrated the slope of that tangent line. You can always get the slope by going over 1 unit in the x direction, and the slope will be the amount that you have to go up or down after going 1 unit to the right to get back to the line, right? So in this case, I have to go down 0.31 units to get back to the line. So the slope is negative 0.31. If I move the point over here, we get a different tangent line, and you see the slope is positive. I have to go up 0.51 units to get to the line. And this makes sense because slope is just rise over run, and if you make the run equal to 1, then the slope is just equal to the rise. Right, so that's what we're seeing here. Now, that's also related to something else, because we know that the slope of the tangent line is the derivative of the function f. So I could have labeled this f prime of x. All right, so that's what we will want to be thinking about here. Okay, so just view this as f prime of x. It's the same thing. So the slope of this line is the derivative of the function at that point, and that is the number that we're seeing here, okay? Now, we're talking about concavity. Concavity has to do with whether the derivative, this number, is increasing or decreasing. So let's see what happens. I'm going to take this point, let's drag it over to the left first, and now I'm going to start moving it to the right. Now, when the slope comes into view, I want you to check, is the slope, let's see if I can move this smoothly. There we go. Is the slope increasing or decreasing? Well, we can see that the value of m is going down. It's decreasing. So the derivatives are decreasing. Now, if the derivative is decreasing, we just said from the definition that the function is called concave down. So the function's concave down over there. Now, if I keep going, now look at the value of m. Is it increasing or decreasing? Well, it's negative. It's going up. It's going up. It's increasing. So this is an example of a place where the function is concave up. So the function was, I think I have to move the graph over a little bit to see the value of m now. The graph was concave down, now it's concave up. That m changed from being decreasing to being increasing, right? So the function went from concave down over here, the m is decreasing, to concave up over here. Now the m is increasing. So where did that concavity change? Well, it changed right here. Right? So there is a point where the concavity changed, where the m was decreasing and now it became increasing. And that's another important point. That point is called an inflection point. Let's read the definition for inflection point. If f is continuous at a number a, and f changes concavity at a, the point a comma f of a, that point on that graph, is called an inflection point. And so what we just saw was that there's an inflection point at 0. In fact, the point is 0 comma 0 for this graph. So you can see concave down until we get to here, and then concave up going past that point. And I think we can kind of see a geometric picture of concavity here. Notice that the function, the graph, is bowl-shaped down. It's arcing downwards. It's like a frowny face, right? It's a frown. Here, it's bowl-shaped upwards, right? Like a smile, right? That's concave up. And when it's right in between being concave down and concave up, that's called an inflection point. Okay, so let's look at some examples. Use the graph of each function. We've got a function f and a function g here, and we've seen these in the previous videos. But in this video, we're going to be looking at the intervals on which the function is concave up or concave down. So we're going to be thinking about concavity, all right? So let's look at this function f, all right? And I'm going to cover up g, and we're going to write down the intervals for concave up and concave down. Okay, so let's see what's going on here. As I start over here, and I come down this part of the graph, one quick way to check is just, is it bowl-shaped up or bowl-shaped down? Well, it's like a bowl opening upwards. So that's what we would call concave up. Another way to think about it is to imagine the slope of the tangent line. Right? The slope of the tangent line is increasing. It's negative over here, it's 0 at this point, and it's positive over here. It went from negative to positive, and so that's what it means to be concave up. So how far does this concave up go? Well, until we get to here, this point, it becomes, that's when it changes, and now it becomes concave down up to here, all right? So we see it's concave up from 0 to 2. I'm looking at the values on the x-axis to determine these numbers, 0 to 2. And then it's concave down from 2 to 3 to 4. 2 to 4. Okay? And then what happens over here? Well, the derivative is pretty steep over here. It's pretty big, but it's less steep over here. It's a little bit smaller. The derivative has decreased. This is bowl-shaped down. It's concave down. So this continues to be concave down over here. So from 4 to 5, 6. Notice that we did not include the number 4. You don't just write from 2 to 6, because there's this one point here where we actually don't have any concavity. And just to check here at the definition, the function needs to be differentiable in the interval to have a concavity, right? But at that point, the function is not differentiable. There's a kink there. So we can't include that number as part of the interval of concavity. So that's why I've jumped over that number 4. Okay? Now, what about the inflection points? Let's do that. Let's see where those are. That's where it changes concavity. Well, I can see it changed from concave up to concave down at the number 2, right here. It was bowl-shaped up. Now it's bowl-shaped down. And what is this point? Well, it's the point 2, comma 1, 2, 3, 2, comma 3. Now, it looks a little confusing because over here I was using interval notation, but this represents a point, all right? So keep that in mind. These are intervals. This is a point. It's unfortunate that in mathematics we have the same notation for both things, Don't confuse these, all right? This is x comma y, a point. This is an interval ranging on the x-axis from one number to another number, all right? Don't confuse those things. All right, let's look at the function g. Okay, so let's look at concavity, all right? So let's move from left to right here. From here to here, going to here, this looks like it's bowl-shaped down until we get to here. So from 0 to 2, it's concave down. 0 to 2. Right, now what happens here? Well, now it's bowl-shaped upwards, right? So it's bowl-shaped upwards from 2 to, actually, you know, it looks like it starts arcing down like right here, preceding this line. So I'm going to go to 3.8. So from 2, 3.8, it's bowl-shaped upwards. It's concave up. And what happens after 3.8? It's bowl-shaped down. Notice the derivatives are decreasing. So here, from 3.8 to 4, 5, from 3.8 to 5, it's concave down. And then what happens after 5? Well, now it's bowl-shaped up again, so that's concave up. So from 5 to 6 to 7, it's concave up. Okay, and where did it change concavity? Well, it changed concavity right here at the point 2, 2. And it also changed concavity, let's see, it's concave up, at 3.8. So at 3.8 comma, what is that? That's about halfway between this number and this number. Halfway between 2 and 3. So 3.8 comma 3.5. Now notice, I don't put a union symbol here, right? Because again, these are not intervals, so it doesn't make sense to union them. I'm just listing points, all right? So I put a comma. Doesn't make sense to use a union symbol between points. And there is another inflection point at the point 5 comma 4, which I'm seeing right now as I'm editing this video. So let's include that. All right, so that is the concavity of this function. Okay, well, what else can we say about concavity? Well, we have this theorem, test for concavity. What does it say? It says, let f be a function that is twice differentiable over an interval I. Part 1, if the second derivative, f double prime, of x is greater than 0 for all x in the interval, then f is concave up over that interval. If the second derivative at x is less than 0 for all x in that interval, then f is concave down over that interval. Now, does this make sense? Well, let's think about what it means to be concave up, what the definition was. Right? A function is concave up if the derivative is increasing. But we know that for a function to be increasing, it means its derivative is positive. So if f prime is increasing, that means the derivative of f prime, that's f double prime, must be positive. And that's what this is saying. F double prime is positive. That means it's concave up. And over here, we're talking about concave down. Well, if we go back, to be concave down means the derivative is decreasing. Well, we know that a function's decreasing if its derivative is negative. So that means the derivative of f prime is negative. Well, the derivative of f prime is f double prime. And that's what we're saying here. If f double prime is negative, that means that f is concave down. So this is a simple extension of the idea of increasing or decreasing applied to f prime, and then using the notion of concavity. All right, so that's where this theorem comes from. The exercises. Find the intervals of concavity and the inflection points for these functions. Now, these functions should be very familiar to you if you've seen the last few videos. All right, these are the same functions we were working with. So let's start with the first one. Okay, so here's my function. Now we want to find the concavity and inflection points for this. All right, well, that means that we're going to be looking at the second derivative, right? So I got to compute two derivatives. So in the last videos, we computed the first derivative, so let's just write that down really quickly. And what we'll do now is we'll compute the second derivative, f double prime. Well, the derivative of this is 6x, the derivative of this term is 6, and the derivative of this term is 0 because it's a constant. So here we have f double prime. So we're looking for where f double prime is positive or negative. So what I'm going to do is I'm going to look for where this is equal to 0, and we'll solve for x. Well, I don't think much solving needs to be done. I think it's obvious that x is equal to, yeah, you guessed it, 1, right? So solving that gives us x equals 1. Okay, so what I'm going to do is I'm going to draw a number line over here. And I only have one number to plot, the number 1. Okay, so I'm going to be looking at the sign of f double prime. In the last videos, we looked at the sign of f prime, but here we want to know the sign of f double prime. So let's plug in a number less than 1 here. If I plug in a number less than 1, like 0, it's my favorite number, in for x, what do I get? Well, 6 times 0 minus 6 is negative 6. All that I care about is the fact that it's negative. I don't really care that it's a 6, right? It's negative here. And if I plug in a number over here, say 2, I get 6 times 2 minus 6. Well, that's equal to positive 6. I don't care that it's positive 6. I just care that it's positive, right? So, okay, that's the sign of f double prime. So we see that f double prime is negative on this interval, from negative infinity to 1. So that is where f is concave down. And f double prime is positive on the interval 1 to infinity. So that is where f is concave up. All right, so we have these intervals of concavity. We were also asked to find the inflection point. So let's see if we can find that. Well, that is the point at which the function changes concavity. Well, we see it changed from up to down at x equals 1. Now, 1's not a point. We want the point on the graph. So we need the y-coordinate. This is the x-coordinate. To get the y-coordinate, we plug this number in for x. Now, we want the point on the graph of the function, right? So don't plug it into f prime, don't plug it into, or f double prime, don't plug it into f prime, plug it into the original function. We want the point on the original graph. So we're going to plug 1 into this function. And when we do that, we get 1 minus 3 minus 9 plus 4, negative 7, right? So the inflection point is 1 comma negative 7. Okay, so let's take a look at the graph of this function and just verify that this makes sense. So you can see this is the graph of the function we were working with. We can see that it's concave down, bowl-shaped down, until we get to about here. And that is at 1. And after 1, it becomes bowl-shaped upwards, concave up. And that's just what we verified. So we can see it's concave down from negative infinity to 1, concave up from 1 to infinity. And the place where it changed concavity was this point right here, the point 1 comma negative 7. We'd be negative 7 on the y-axis here. So that is the inflection point right there. Okay, so let's go to number 2. Find the intervals of concavity and the inflection points for this function. And we're given a hint for the second derivative here, all right, which we're going to need. That hint is not necessary. You can totally compute the second derivative on your own. I just wanted to point this out that it can be simplified into this form, because when you compute it, you may not get it in this form. So a good exercise for you to do is go ahead and compute both derivatives of this function, right? And make sure you see how to simplify the second derivative so that it looks like this, all right? So yeah, this is what we're working with. We're working with this function, and in the last few videos, we computed the derivative, and we found it to be as follows. And when you compute the second derivative, we'll just follow the hint here. All right, so there's our second derivative using the hint. Or, like I said, it's not hard to get there from here. Just use the quotient rule on this function. It's a good exercise. Go ahead and do that, and make sure you can simplify it to this. Okay, so we want to know about the concavity, and so we will look at the sign of this function. We'll do it the same way. We'll look to see where this function is equal to 0. All right, well, it can only be equal to 0 when the numerator is equal to 0. And so we're going to be looking at that. All right, so where can this numerator be equal to 0? Well, it's already factored, so that's nice. So if x is 0, the numerator will be 0. And if x is equal to plus or minus root 3, this will all be 0. So we have three places to look. Okay? So that's how we'll break up our number line. Okay? Now, there's one other place you should look, and that is where this function is undefined. That's another place where it can change from being positive to negative. However, as we pointed out in the last videos, this denominator can never be equal to 0 because it's 1 plus a non-negative number. And so we don't have to worry about this expression being undefined. However, I'll point out that that is another place that you should break up this line if such a place existed. If this were undefined somewhere, that would be another value you'd have to include here. Okay, but we don't have to worry about that for this function. So, okay, so let's just check the sign of f double prime here. Okay, so let's pick a number over here, like, I don't know, negative 4, right, is less than negative root 3, right? So, actually, negative 2. Let's use negative 2. Okay, so if I plug in negative 2 for x, what do I get? Well, I get negative 4 times 2 squared minus 3. Well, that's just 1, so negative 4. And then the bottom's positive, so I have a negative number divided by a positive number, and so the whole thing is negative. Okay? What about a number in here? Well, how about negative 1? If I plug negative 1 in here, I get negative 2 times 1 minus 3. That's negative 2. That's negative 2 times negative 2 is positive 4. Divided by something positive is still positive. Okay, if I plug in a number in here, like 1, I get positive 2 times negative 2, so that's negative 4, divided by a positive number is negative. And over here, I'll plug in 2, right? 2's in this interval. So 2 times 2 is 4, 2 squared minus 3 is 1, so 4 times 1 is 4, divided by something positive is still positive. Okay, so here's what I'm seeing. So it's concave up when f double prime is positive. So that's going to be on this interval and on this interval. Right? And it is concave down where f double prime is negative. So on this interval and this interval. Okay, that's a lousy infinity, but that's supposed to be an infinity. It looks like a pair of glasses. Okay, so there we have concave down. Now notice it's where f is concave down. Don't write f double prime here, right? We're talking about the original function, but we're using f double prime to get there. And where does the concavity change? Well, it changes here, here, and here. So there's 3 inflection points. Okay, so the inflection points are as follows. Negative root 3 is the x value. How do I get the y value? Well, I have to plug this number in to the function to find the y value. All right, well, if I plug in negative root 3, let's do the denominator first. Root 3 squared is 3, plus 1 is 4. So the denominator is 4. The numerator is negative root 3. So it's negative root 3 over 4. All right, so, oops, negative root 3, comma, negative root 3 over 4. Another inflection point happens here at 0. What happens when I plug in 0 into the function? Well, the numerator is 0, so the whole thing is 0, right? So the point 0, 0 is an inflection point. And then finally, if I plug root 3 into here, I get root 3 over 4. So that is my last inflection point. All right. Now you'll notice that here we alternated, and that'll often happen, but that will not always happen. Don't think that just because you have minus here, you know the rest, right? I can give examples where you can have a minus here and a minus in the next interval, all right? So don't assume that these are going to alternate plus minus plus minus. Okay, so let's take a look at the graph of this guy. And here we see, okay, so you see it's kind of bowl-shaped down over here. right, until we get to about there, and then it starts being bowl-shaped up. So that's our concave down up until here. Well, this number is what we found was negative root 3, right there. And then after negative root 3, it starts being concave up, right, until we get to here, and then it's concave down again. So that was our other inflection point at 0. Now it's concave down until we get to about here, which is what we found to be root 3. And now it's concave up again over here. And we have our inflection points at negative root 3, 0, and at positive root 3. All right, finally we have our third example here. And so we're dealing with this function. We need to compute the derivatives. So we did this in the previous videos for the first derivative, so let's just write that down quickly. And now we do the second derivative. Okay, and we're looking to see where this guy is positive or negative. So we'll look to see where it's 0 first. All right, so let's set this equal to 0. And we'll solve for x. So let's let's add cosine x to both sides, and then divide both sides by cosine. So what do we get? We get this, but what is this equal to? This is the negative of tangent x. Or in other words, for negative tangent x to equal 1, that's the same thing as saying that tangent x equals negative 1. So we're looking for the angles x in this interval that have a tangent of negative 1. And so like in the previous videos, think about the unit circle here. Tangent tells you if you pick an angle x, right? Tangent gives you the slope of this line, right? And now we want the line with slope negative 1, which is just how I've drawn it, right? So the tangent is the slope, so we want that line to have slope negative 1, and you can see that means that this angle here has to be 45 degrees, or pi over 4 radians. So if this is pi over 4, what is this? Well, we know that from here to here is pi, so if I subtract pi over 4, I get to the angle that I want. So pi minus pi over 4, that's 3 pi over 4, is one of the values for x. All right, so that's going to be one of the places we divide this interval into. Now, we're restricted to the interval from 0 to 2 pi. And we're going to divide it here at 3 pi over 4. And now there's another value of x that works here that makes tangent negative 1, because I can also look down in this direction, right? That also has slope negative 1, but that corresponds to the angle that goes all the way around like this. That's another solution, all right? How do I get this angle? Well, this angle here has got to be pi over 4 radians, 45 degrees, right? So I'm 2 pi radians all the way around the circle minus pi over 4, right? So that is 7 pi over 4. So that's going to be this over here, 7 pi over 4. Okay, and we're going to be looking for the sine of f double prime here. Okay, well, in this interval, I just need an angle in here. Let's pick this one. It's really nice, pi over 2, right? Pi over 2 is between 0 and 3 pi over 4. And pi over 2 is easy to evaluate these trig functions on, right? Sine of pi over 2 is 1, and cosine of pi over 2 is 0. So we have negative 1 minus 0. That's negative, right? Over here, I need an angle in between this and this, right? Well, what about this right here, pi, right? So I'll just plug in pi. Sine of pi is 0, and cosine of pi is negative 1. So I have 0 minus negative 1. That's positive. It's positive 1. And then between 7 pi over 4 and 2 pi. So I need an angle in here, right? What if I consider an angle of pi over 6 radians over here? That's less than the pi over 4 that would get me this way, right? So that would be negative pi over 6 radians. So sine of negative pi over 6 is at negative 1/2, And cosine of negative pi over 6 is root 3 over 2, right? So I have negative of negative a half, so that's positive a half, minus root 3 over 2, so 1/2 minus root 3 over 2. Root 3 is bigger than 1, so this whole thing is negative, right? I don't care about its exact value, I just need to know what the sign is. Okay, so we have enough information. Hopefully I have enough room to write these things down. So we see that f double prime is negative here and here, so that's where f is concave down, and it's positive here, so that's where f is concave up. So f is concave up on this interval, on the interval 3 pi over 4 to 7 pi over 4, and f is concave down on this interval 0 to 3 pi over 4, and this interval 7 pi over 4 to 2 pi. And where are its inflection points? Well, we have one here and here. So these are the x-coordinates of the inflection points. To find the y-coordinates, we have to plug these x-coordinates in, right? So, okay, so here we go. 3 pi over 4. Sine of 3 pi over 4 is root 2 over 2. Cosine of 3 pi over 4 is negative root 2 over 2. You add those, you get 0. So the inflection points, 3 pi over 4, comma 0. And what about 7 pi over 4? Well, sine of 7 pi over 4 is negative root 2 over 2. Cosine of 7 pi over 4 is positive root 2 over 2. So again, when you add these, you get 0. So there we have our answers. And let's take a look at what the graph actually looks like. We're only looking at the interval from 0 to 2 pi. So let me just get that a little bit more in range here. Okay, cool. So we can see it's concave down until we get to here, 3 pi over 4. That's what we said. And then that we have an inflection point there, 3 pi over 4 comma 0. And then it's concave up until we get to here. And that's our next inflection point, 7 pi over 4. And then we're concave down until we get to, well, we stop here because that's the end of the intervals, right? So that's our last bit of concave downness. And that verifies exactly the stuff that we wrote here. Okay, well, I hope you learned something here about concavity and inflection points, and we'll be using these in the next video, the very important video about the second derivative test, the most useful of all the tests. It's the one people most readily go to if they want to find maxes or mins. So don't miss that video coming up next.